Greetings to you. This is Lynnate Nazziwa together with Marvin Benjamin Kivumbi, students at UTM, and this is our first assignment submission for system modeling and analysis of a two-wheel balancing robot. So to start off with our modeling, considering the system on this other slide here, we have our system broken down into two parts. The first one is the wheel and the second one is the main body of the system. So we are able to resolve our forces and angles in accordance to what we want to achieve, and we come up with differential equations, and later on we come up with state space equations, which are these two equations here. We are also able to model our geared motor, and come up with equations as well. Now, combining these two, we have a finite time domain equation and a finite frequency domain equation. These two are our state space representations of the entire robot. And in our state vector, we have x, which is our displacement. We also have x dot, which is our velocity. We also have theta b, which is our tilt angle for the robot body, and finally we have theta dot, which is our angular velocity for the robot body. So moving on to our simulation in Matlab, we are able to get the various parameters that are required in accordance to our model here from the datasheet of the motor, and those include some like the armature resistance, the armature torque constant, the armature back EMF constant, moment of inertia, and many others, as you can see here. So on running this code, before we run this code, we are able to write out these matrices into their particular formats, as you can see, and we come up with matrices A, B, C, and D, as you can see. So we then write our state space matrix, which is right here, and finally change it into a transfer function, as you can see here. So on running our code in Matlab, we are able to get these particular graphs representing our different states. The first state is x, the next state is x dot, the next one is theta dot, and finally theta dot, So these are when we have an open system. And right here in our command window, we are also able to get the different poles of the system, as you can see. But being that our poles, as you can see, we have a 0, we have some positive values, this clearly concludes to us that the system is unstable. In addition to that, we are able to model our system in Simulink. So this is our system in Simulink, and as you can see, we have our input here, which is VA, as compared to what we had before. From this equation, you can see that VA is our input to the system. So we are modeling our VA as a step input to the system, and here we have our outputs. The first output is X, the next output is theta B, and this is what we feed into our scope to be able to view on the scope. So when I run the model in Simulink, we are able to get graphs that characterize the behavior of our system. So this is what we have for the graphs. We have theta B as the red graph and X as the blue graph. So we can see that both of them are exponentially big values, and they tend to converge at the end of the stop time, towards the end of the stop time. And this is another factor to prove to us that the system is very unstable. Um, However, we are also able to view the system in a mode where we have no feedback fed into the system. Actually, this was a scenario where the feedback is fed into the system. So we shall simply remove this feedback. For example, for theta b, we shall remove this feedback to see what happens for the system. If we remove this and remove the feedback from x as well, which is this, um, we are able to get a system in its original state, which could be the open loop system. And then we can now run again to see the difference in the graphs or any other changes it could cause. So when we look at our graphs, majorly the value has just grown a little bigger. The magnitudes of theta b and x have just grown a little bigger, meaning that the magnitudes are reduced when we have feedback. Theta b going back to this, and sorry, x going back to this, and theta b going back to this into the system. Though this does not confirm to us that the system is stable. This actually confirms that the system is very unstable, hence a need for a controller to make the system stable. This also signifies to us that the robot cannot balance without a control system input into the system block diagram. For example, here you can see we only have the input, the output, and the system. We do not have a controller anywhere. Maybe to further highlight more, a stable system is one that produces a bounded output for a given bounded input. And as you can see for this, we have a step input, which is meant to be our bounded input, though we are not getting a bounded output, hence the system is unstable. And also, an unstable system is a system that's out of control. Now, for stability, looking at the poles we got in the Matlab file, right here, we are also able to see that we have poles of the robot. Okay, this is our transfer function. This is robot TF. So we have poles that clearly show that the system is not stable, and hence a need for a control system for us to be able to have our system stable and for the robot to be able to balance. In conclusion, there are a few controllers that we've been able to look at that could help out to stabilize the system, hence have the robot balance. The first one is the state feedback controller, and the second one is the PID controller. Manipulating the different values and variables in those two controllers, we could be able to have our robot balance and attain stability. Otherwise, Matlab is able to help us analyze system stability basing on the poles, and also depending on the nature of the responses, the output responses, we're able to see changes, varying changes depending on our inputs. We could also take another scenario here where we input a different time, like 3 seconds, and we try to run and see what happens to our graphs. So when you look at our graphs, we have the same shape as what we had before. They both exponentially grow big, which is our x and theta b both exponentially grow big with increasing time and tend to converge at the end of the stop time, which shows us that no matter the time change, we won't have a stable system. The only way to have a stable system is by adding a controller. This also draws to a conclusion that a balancing robot clearly requires a controller for it to be able to work. Without a controller, a balancing robot cannot achieve its goal. In short, it cannot balance. Thank you so much. That's our submission.